Hi, my name is Srinivasan, and I'm going to be talking about adaptive submodular maximization under stochastic item costs. So what is this problem about? So what we have in this problem is a set of items, and each item has a cost, and each subset of items has a utility value, and this value is non-negative and it is non-decreasing. So as you add more items, the utility will only increase, or at least not decrease. And your goal is to pick a subset of items which maximizes the utility without exceeding a given budget. So you have a knapsack style constraint. And what is going on in this work, what is going on in this paper is that we consider a setting where both the costs and the utility function can be stochastic. And the utility function additionally has submodularity-like properties, and we will define what this means in a minute. So here's what we're going to do in this talk. We will take a look at the different types of utility functions that we care about, then the different types of knapsack constraints that we care about, and then different combinations of these utility types and knapsack types give rise to different settings of this problem. So we will look at what previous works studied and how our work generalizes those settings. And then we will describe two policy. First is the well-known greedy policy, and the second is a mixed policy. This is a new policy for solving this problem. And then we will finish with an open problem. So let's take a look at the different types of utility functions. The first type is a modular utility, right? So this is the simple case. You have each item has a utility value, and when you pick a set of items, the utility value is simply the sum of the item per item utilities. We can generalize modular into submodular utility functions, and as you know, submodular functions have this diminishing returns property. So suppose you have picked a set of items, it's called S1, you have picked the set S1, and you add a new item E to it, you get some marginal utility. And this marginal utility is going to be more than what you would have gotten if you had added E later on. So you pick some more items and then add E and then see its marginal utility. It wouldn't be as good as what you're getting right now. So adding now is better than adding later in terms of marginal utility for the same item. And there are many applications where the utility function turns out to be submodular. So there's a way to generalize this submodularity property. So in many other applications, the submodularity property holds only approximately, doesn't hold exactly. And the degree to which the submodularity property holds is quantified by the submodularity factor alpha between 0 and 1. So if alpha is 1, it is submodular. If it's 0, it's very far from submodular. There's another way to generalize submodular functions, and this is the so-called adaptive submodular functions. It's adaptive because essentially the utility function itself is now stochastic because items now have random states, and the utility function is determined by these collectively by the random states of all the items. And here is an example, right? So think of a sensor network, and you have picked a particular sensor, and the sensor can turn out to be in a low state or in a high state. So in the low state, in this example, it has covered 3 locations, and in the high state, it has ended up covering 5 locations. So its coverage is more. So intuitively, what is going on here is that no matter, suppose you pick this set of items and you observe their states, then for a new item E, its marginal utility in expectation is going to be better now than later. The keyword here is in expectation. So in a probabilistic sense, the utility function is submodular. There are numerous applications of adaptive submodularity. I've just listed a few here. Finally, we have this notion of approximate adaptive submodularity. So once again, items have random states and the utility function is stochastic, and the submodularity property now holds in both an approximate and a probabilistic sense. So, and once again, we have this factor alpha that quantifies the extent to which this function resembles a submodular function. All right, so those were the different types of utility functions. We can also look at the different types of constraints we can consider, right? First is the cardinality constraint. So we can think of this as each item has a unit cost. The cost of each item is 1, and you just want to pick a certain number of items without exceeding the budget B. So B is a positive integer, and you want to pick at most B items. The next is the knapsack constraint. So this is the familiar knapsack constraint. Each item has a fixed, non-uniform cost. The cost need not be equal. And the total cost of the items should not exceed your knapsack capacity B, which is some fixed positive value. And next, we have the stochastic fractional knapsack. So what is this setting? So in this setting, item costs need not be fixed. They can be random. And in this paper, we assume that item costs are independent. We can vary independently at random. And the constraint here is that the total cost of items that you pick should not exceed the knapsack capacity in expectation. That's the stochastic fractional knapsack. And finally, you have the stochastic knapsack. Once again, you have item cost that can be random, but this time you want the total cost of items you pick to not exceed the capacity with probability 1. So no matter what the realization of item cost turned out to be, you want the total cost of the items you pick to be within the knapsack capacity B. So what is the setting that we actually consider, and how does it differ? So here's all the different utility function types have been considered before, but most of the existing work considers the cardinality constraint, right? So the difference in this work is that we are able to handle the cases where both the utility function and the item costs are stochastic. That's the basic contribution of this work. In particular, when the knapsack constraint is the stochastic fractional knapsack, so the item costs are random and you want to keep it within the budget in expectation, we can actually solve the maximization of all these different utility function classes, and we basically show that the greedy algorithm works with probably good guarantees in for all these different utility classes. More interesting, perhaps, is the stochastic knapsack version. So there, the costs need to be within the budget with probability 1, and the total cost needs to be within the budget with probability 1, and item costs can vary at random. So this is in fact the first work to develop probably good algorithms when the utility function is not modular and the constraint is a stochastic knapsack constraint. So we solve this problem for submodular utilities and adaptive submodular utilities, and we provide the first algorithm with probably good guarantees in this setting. So what are these policies, right? So first, let's look at the greedy policy. As I said, it works for the fractional stochastic knapsack setting. And the idea here is that basically, let's say you pick this set of items and you've seen their states. So you can greedily pick the next item, which maximizes the ratio of its marginal utility and its cost in expectation, right? So it's a utility per cost maximization. So that is the classic greedy algorithm. But in the numerator, you have an expected marginal utility. In the denominator here, you have the expected cost, and that is what is getting maximized. And in fact, this greedy step doesn't have to be exact. This greedy maximization step, selecting an item greedily, can itself be approximate with a factor beta, and we can roll this factor into our guarantees. And basically, we keep doing this. And if we come to a stage where we are about to exceed the knapsack capacity in expectation, then we just round the last item probabilistically. So we toss a coin, and if it turns out one, we are heads, we pick it, and if it turns out tails, we drop it, and we set this bias so that, you know, in expectation, our cost equals the knapsack capacity. Randomized rounding. That's a greedy policy, and it works for the fractional stochastic knapsack setting. So what about the stochastic knapsack setting? So here we want, with probability 1, we want to be within the budget. So the randomized rounding is not going to work. And here we use a new policy. It's called the mixed policy, and there are two components to this mixed policy. So the first component is called light. So this is a policy in itself, and the idea here is to first of all transform the item cost. We describe the specific transformation we use within the paper. It's from an existing previous work that we take this transformation, previous work on stochastic knapsack. So we transform the item costs, and we can now use the greedy policy described above with this transformed item costs. So that's the first component. That's the first idea. The second idea is that we choose a single item that maximizes marginal utility in expectation without worrying about cost at all. So that's the second component, the second idea. And the mixed policy basically is a probabilistic mix of these two different policies. It mixes with some probability, it chooses light, with the complementary probability, it chooses singleton, and that is the mixed policy. And one thing to note here is that as soon as you exceed the budget B, the algorithm stops and discards the last item that was selected. So whether it's light or whether it's singleton, that's how the policy works. So it's you're guaranteed to be within your budget B with probability 1. And as we describe in the paper, these policies have probably good guarantees for the settings studied in our paper. All right, so that brings me to the last point, which is the open problem, right? So in particular, the setting that is kind of particularly interesting is this combination. If you don't have this fractional knapsack situation, so if you either want if you either have fixed cost and the knapsack setting, or you have stochastic cost and the stochastic knapsack setting, so you cannot fractionally round an item. So if you are in the knapsack or stochastic knapsack setting, nothing is known about optimizing approximate submodular utilities or approximate adaptive submodular utilities. So those settings actually remain open. So this combination actually remains open. So that's basically the end of my talk. Thank you.